Seems like we're talking about performance every Dyalog conference, right? Yes? Okay. As Jay mentioned in his technical roadmap yesterday, we have a suite of QAs called PQA or Performance QA, which we run every day. Takes 12 and a half hours to run on a dedicated machine. It's a suite of benchmarks, about 14,000 benchmarks, divided into 136 groups. And to summarize the results, we have these graphs in which the horizontal axis are the 136 groups, sorted by the group means. The logarithms of the group means. And if it's above the axis, it means the version 15. In this case, is comparing version 15 to version 14.1. So if it's above the axis, it's colored blue, and it's good. Love the blue mountain. And if it's below the x-axis, then it's color red, and the red pit is not good, because from user feedback, the blue does not excuse the red. So we ran this on January 22nd this year. So it's encouraging that version 15 is overall 17% faster than version 14.1, but the amount of red is not acceptable, especially this deep. Is there a laser pointer? Ah, yes. Especially the deep pit. Okay, so we started working on it. This is about a month's worth. The font is too small for you to see the details of the numbers, but the important thing to note is the decrease in red until on February 26th. We have an unprecedented event in the history of computing. Or at least Dyalog computing, where there's no red. Yay! I made a GIF, is that how you pronounce it? GIF or GIF? GIF, a GIF movie of this, and the results were not as nice as I had hoped, but I'll keep working on that, because it is useful to be able to see the whole progression as a movie. So now I'm going to focus on the first and the last. That's about a month's worth of work by the whole team. So as I said when we began, it's overall it's 17% faster, and at the end we're 25% faster. And no red at the end. At one of the Middlebrook conferences, somebody who I shall not name, but he says, after each release, we should shoot the implementers. Because if we keep tinkering on the interpreter at this point, it can only get worse. So we should have stopped at that point. Anyway, this is our benchmark, our suite of benchmarks, and your mileage may vary. So if you have applications that are important to you, please send us the information, and we can try to do something about your application specifically. The other thing to note is that these numbers on the bottom focus on groups that are 2% faster than before or 2% slower than before, because we have found that especially on small expressions, like expressions that take maybe 1 microsecond to run or less, differences of less than 5% are not reliably reproducible. Running benchmarks is harder than it looks or appears, especially on small expressions. We had actually invited one of these program traders to talk to us about, among other things, benchmarking. And these are people who care about, for these people, 1 nanosecond is a long time. And he knows the difference in transmission speed in copper versus fiber. And he knows the midpoint between the New York Stock Exchange and the Chicago Exchange to better place their computers or something. But he was not able to, he was either not willing or not able to tell us benchmarking techniques that are better than what we use. Okay, so another thing to note is that inversion, the amount of blue is gratifying, but it's probably not going to be reproducible in the next release, because one of the things that account for the blue is the in version 15 we switched to a new release of the Visual Studio compiler. So in version 15 we're using Visual Studio 2015. In version 14.1 we're using Visual Studio 2005. So the high peaks are probably due to individual speedups, and the overall improvement is probably due to the new compiler. And so the new compiler, this new C compiler, the Visual Studio C compiler, has some optimizations. Unfortunately, it also comes with what Jay calls pessimizations. And among them are slowdowns in memcopy and memset. Nasty. And, I think it was at this point that we killed the memcopy and memset problem when the pit went down. Okay. So as far as specific speedups, in version 15, we had an unusually long list of speedups. There's about 60 individual speedups. And yes, these slides will be available from the conference website. You can download it and meditate on the details at your own leisure. But I would like to focus on some specific ones to give you an idea of how we decide what to work on. So if the speedup factor is less than 2, it's usually not worthwhile for us. Plus, if the factor is 2 or more, then there's no argument on whether it's faster or not. Okay. If it's less than 2, there has to be some other reason to justify it. So from experience, sorting and searching quite often has an outsized performance impact on an application. So if it's related to sorting or searching, that's a good reason for working on something. A magic function is a piece of APL code in the C source of the interpreter. And is Aaron here? No. Anyway, oh, yes, Aaron. So I should just send you all the magic functions in the interpreter as benchmarks, because they're prime candidates for compiling. Yeah? So if something is already coded as a magic function, or uses something, or it can be implemented as a magic function, then it's a good reason for doing it as a speed up. And small int results are, well, Dyalog has 1 byte and 2 byte integers, as well as the more usual 4 byte integers. And we want to exploit that to a greater extent than we already have. And small domain is kind of a dynamic concept because, yeah, something can have, for example, a vector of integers can have small range, like the difference between the maximum and the minimum is small relative to the size of the array, then I call that small range. And we have algorithm to exploit that. And Boolean or bit arrays, of course. I should rename that to be Aaron Su Specials. Anyway, bit arrays we want to work on. And special cases of operators. So for example, is that mix or split? Mix? Mix, yes. So it's used in magic function. And as well, it's important in itself. You know, mix is kind of a general thing, but in specific cases, you can actually do some quite nice speedups. But specific doesn't mean unusual. I mean, it's specific but common cases. So, oh, and I must mention the plus dot times. This came for free from the Visual Studio 2015 compiler, because it's able to recognize the way we coded plus dot times in C, which I call row at a time rather than the conventional row by column, or it's the CDC star algorithm. So the factor of 3.3 came without any changes to the C source. I guess we can take a little credit for it because that's the way we coded the C in the first place. Yeah. Okay, over to you, Jay.
Am I on? Am I on? Yep. Right. Okay. You're going to get sick of seeing these graphs. Roger's already talked about performance QA, so I'll just let you appreciate the beauty of the Blue Mountain and move on. I want to talk about one or two particular speedups that Roger hasn't mentioned, first in version 15, and then a few things that we're doing or planning to do in version 16. And the first thing is a feature, I think I mentioned this yesterday in the roadmap address, but I just want to go through it in a tiny bit more detail. We have this new feature called hashed arrays, which allow you to mark a particular array, typically a long vector or something like that, as something that you're going to do frequent lookups in. So you say specifically, I want this thing to be hashed, or I use the term hashed loosely. I want the interpreter to generate a hash table or lookup table or something because I'm going to be doing a lot of lookups in this thing. Previously, we did have a way of doing this by forming a little derived function where the argument is bound with a search function. This new system is better because it lets you use the same hashed array with whatever search functions you like. And most importantly, because it supports updating the array that has been hashed. You can append items to your vector or append rows to your matrix, and you can use this new idiom, drop commute gets, which I call chop, for cutting items off the end of your vector or matrix. And, right, so the old way you might have done this is by naming a derived function and then applying it to a bunch of different arguments that you want to look up. The new way is to use an I-beam to create a sort of alias for the array. A was your original array, B is kind of a hashed copy of that. And then you can use that with various different set functions, and you can modify the data in B. You can append to it, and you can remove stuff that you've appended. And in particular, it's worth pointing out that this new chop idiom, although it was motivated by the hashed array stuff, is useful in its own right. It's very similar to the append idiom. It is the fastest way of trimming things off the end of a vector or off the bottom of a matrix because it works in place. It doesn't have to copy the data in order to do your operation. So if you're talking about taking a couple of items off the end of a 1,000,000 element vector, then it can easily be 1,000 times faster than just using drop on its own. And although it looks rather cryptic, drop commutes get, it has to be expressed in that way so that the idiom system can handle it. What we're really doing here, vec drop commute get neg2 is saying, please assign to vec the neg2 drop of vec. Yep. Right, on to a few miscellaneous things that are going into version 16. The first is about random numbers, and in particular, if you're interested in generating a whole load of random bits or random Booleans. So, for example, you might do the query of 1,000,000 reshape 2 in quad.io0 to get a load of random zeros and ones. There are two things that are going on here in version 16. The first is to do with the random number generators. I think Richard has probably spoken before about various changes in the random number generators over the last few releases. One thing that's happening in version 16 is that we have this idea that by default the sequences of random numbers we generate are not necessarily reproducible. And the reason for introducing that is it gives us a bit of freedom to change the algorithms. You know, we're not tying ourselves into generating the same sequence of pseudo-random numbers that we generated in all previous releases. And that kind of frees us up to do little optimizations to make the thing work more efficiently. So in version 16, by default, I think I'm right, you get non-reproducible sequences. Yeah, okay. And if you're generating bits, that allows us to kind of generate them, 32 or 64 at a time, whereas previously we were trying to match the old result, which got one number from the random number generator for every bit you want to generate. Now we can do something much more efficient, where you get one number from the underlying generator and use all 64 bits of that and chuck them into an array. So that, we're comparing version 15 here, so 4.5 milliseconds for doing that. We're down to 0.2 of a millisecond here, so that's, a factor of 20-odd improvement. And then once you get to that level of speed of generating the random bits, the way we're generating them is by first generating this vector of 1,000,000 twos and then passing that into the roll primitive. Once we get to this level of speed, the time it takes to generate the intermediate vector of twos is becoming a problem. So as kind of a cute trick, we've got a function train, query reshape. Roll reshape? Roll reshape. Which is specially optimized not to have to generate that intermediate array. And as you can see by the bottom row here, you're getting maybe a further factor of 3 speed up out of that. So that's two independent things that work quite nicely together if you're into generating random bits. Next up, namespace references. Various people have commented over the years that they would like to use namespaces as a way of organizing their source code. So you might have a utility namespace with all your utility functions in it. It has the unfortunate side effect that if you call ns.foo something instead of just calling foo something, you get a bit of a performance hit just from the fact that you've put it in a namespace and you had to use this syntax with a name and a dot to refer to it. And based on some benchmark where foo is a completely empty tradfun, I was measuring something like 80% slower for putting it in a namespace versus just having the function foo available in your current namespace. And once you start analyzing this, if calling a function in the current namespace costs a certain amount of time, 100%, the extra overhead that you get for calling ns.foo instead comes from two separate things. One is that the parser has to deal with this dot notation. It has to do a little bit more work to work out what you're referring to. That's the parsing the dots here, which was adding an extra 40-odd%. And the other is that as you actually call the function, the interpreter has to do some work to switch into the namespace where that function lives and then switch back out again as you come back. And that was adding almost 40%. So we've done a little bit of targeted work to just try and chip away at those overheads. Firstly, by doing special cases in the parser that recognize the common cases where you're just doing ns dot something. The dot, the namespace dot in its general form is incredibly powerful, and you can have arbitrary expressions to the left and right of it. But in the very common case of just saying namespace dot function, there's a fast case for that, which does a pretty good job of reducing the overhead of that part of it. And we've done a little bit of work as well in the code that switches into a different namespace as you call into the function, which has shaved a bit off the overheads. So I'm hoping there's still more work to do in the future, but as I say, we are trying to chip away at that kind of problem.
If foo was an intensive function, would that still?
I'll repeat the question. I think you're asking if foo did a lot of computation, would you still be seeing this kind of overhead? And the short answer is no. This is only a one-off hit as you enter the function.
I think the concern here is that people would like to take a utility function that does very little and put it in a namespace, utils dot remove duplicates or whatever, and then you pay a price.
Yep.
I just have a quick question.
Steve.
If you refer to a function in a namespace using quad path, would that be the same type of thing or not?
Using what? You would definitely get the second part of the overhead. The first part, you'd probably get a slightly different bit of overhead because it goes through a slightly different path in the parser. We're almost out of time.
Excuse me.
Michael.
Did you refer to namespaces only in the rigid sense, or do you also mean classes or instances of classes?
It applies equally to classes, but in classes there is even more stuff going on as well.
What about include?
What about include? I can't answer that off the top of my head. Not sure.
What does it mean?
There's a system for including the contents of one class in another, one namespace in another, one namespace into another. There is a way of including the contents of one namespace into another.
I heard you, but is it an APL syntax?
I'm not the expert.
In a class definition, :include namespace will bring the namespace into the class.
Okay. Let's move on. Something that came to light because of a certain customer was that selective assignment is a very neat way of modifying particular items in an array. It came to light that our implementation is not as efficient as it could be, and in particular, in the cases where you've got a very large array and you're using selective assignment to modify a very small part of it. So, for example, imagine A is a 1,000,000 item vector and you want to update the first 2 items or or the second and the fourth item. The reason that it's inefficient is because the implementation of this stuff, first of all, generates an index set for the entire array, and then applies these selection functions to that index set, and then modifies whatever indices of the original array you still have left. So in the case where A is huge, it ends up generating a huge index set, and then just taking the first two items and modifying those two. This is, there's clearly room for optimization here. What it means for us in practice is that we have to do a little bit of work for each of the primitives that you can use in selective assignment, of which there are probably a dozen or so. I'm going to overrun a little. So currently this came to light in squad indexing in particular, and that was a relatively easy fix. So in version 16, I think we might have backported it to 15 as well. If you use squad in indexed assignment, that should now work a lot more efficiently. We'd obviously like to do the same kind of fix for, certainly for the most common things where you might be modifying just a small part of the array. So if you're doing takes or drops, just to modify the beginning or end of an array, or if you're doing Boolean compressions and just modifying a few items. As time permits, we'll try and speed up those cases. Boolean algorithms, all I should say is come back after the break. Bob will talk about Boolean algorithms. Some of them we've already implemented. Some of them we will be as soon as Bob's shown them to us. And this is some very speculative work we're doing. I don't know, maybe show of hands, who has tried to use the decimal floating point representation for anything? A few people. Okay. It's not widely used on most platforms, i.e. on Windows, on Intel platforms. It's emulated in software, so it gives you increased floating point precision, but at a very significant performance penalty. We are starting to look at the possibility of changing to a different decimal floating point representation. If you look at the standard, there are two competing representations for 128-bit decimal floating point. We picked one of them. It turns out it's good in some cases, but for actually doing calculations, we're now thinking the alternative format might give you maybe a factor of 2 speed increase on the calculations. So depending on conversations with you guys and what the priorities are, we could conceivably switch to that representation. If we were even braver, there's a 128-bit binary floating point format we could adopt, which I reckon maybe gives you another factor of 2 speed up in the calculations. So these are things we're starting to think about. Certainly no definite plans to change as of yet, but we're looking into it. And what's coming in the future? We have no shortage of work. This is a small snapshot of bugs or issues in our issue tracking system related to performance. You're not supposed to read that, but there are lots of them. We're not short of ideas of things to speed up. So no shortage of work for Roger. Roger mentioned the upgrade to the C compilers. There is a bit, he pointed out that we've upgraded to modern C compilers, so we can't go too much further with that. But there is still some more room to squeeze out of our C compilers. We're not using all the optimization levels that we possibly could on the C compilers, in particular on AIX, actually. I know we've got work to do there. There's still a lot of scope to make more use of modern SIMD instruction sets. For example, on Intel, we use SSE2 quite aggressively, and we use some SSE4 and some BMI. We haven't yet done a lot with AVX, which has been out for a few years now, so there's clear opportunities to speed things up with that. And similarly, the Power 8 architecture, I think, has got vector instructions that we're not doing a lot with yet. And I'm hopeful that as issues like this slowdown on namespace references crop up, please do complain if they're affecting you or annoying you. We should be able to do some sort of targeted surgery on the interpreter to try and reduce the overheads for that kind of thing. Right, we're 5 minutes late for coffee. Sorry.